Okay, today we're going to be looking at the second part of our particle accelerators lesson. So previously we did a discussion on the history of particle accelerators and the early advancements in particle accelerators. Now, in its early days, particle accelerators were basically glass tubes with a array of electrons through a vacuum. This is a very crude and basic form of a linear accelerator, because obviously they're in a straight line, so hence the linear, or a linac, as you may see them called. It doesn't even look like linac. Let's rewrite that. Modern linacs are much longer, and they're no longer made of glass, but they're still the same principle. Modern linacs can be up to, let's quickly show you this image of one. This is a linac in Stanford in America, and this is 2 kilometers long. So they can be, this is 2 miles long. So they can become really quite big and can get particles up to really quite high energies. But we'll come to that later. The principle of modern linacs, we can think about them as an analogy in a battery. So say we place lots of batteries in series with each other. The total potential difference is going to be equal to the sum of each potential difference. And therefore the total energy supplied to the electrons is going to be far greater than from just a single battery by having them in series. So this was the idea behind the first particle linear accelerators. The first linacs were made in the 1920s, and they travelled through a series of tubes called drift tubes. Let's get up a diagram. Let me find my diagram of the... So here is a diagram of the linear particle accelerators. So we have these drift tubes, which are kind of analogous to our batteries. They they're placed at different spacings to allow for the rapidly increasing velocity of the particles. So once the electron leaves the drift tube, this is where the acceleration takes place. And as you can see, the spacing between them changes. Now, as the electrons gain velocity, and as they approach the speed of light, the electrons will start to gain mass. So as electrons gain speed, and as they approach the speed of light, they also gain mass because of the relativistic effects. But also, you no longer need to be changing the spacing between the drift tubes. That can now become constant as it approaches the speed of light. the drift tubes have a AC supply added to them, so you've got a changing electric field. There's no increase in kinetic energy inside the drift tubes. Now, once you get these drift tubes, you see this is negative and this is positive. So as this comes out here, this is going to be negative and this is going to be positive. So this gap here will, because this electron is negatively charged, it'll be attracted to the positive, and that's where you get your acceleration. And it's important that at that point of exiting the drift tube, this is positive so that you'll have that acceleration. Magnets are also placed around the circumference of the accelerator tube to, in effect, repel any stream of particles that kind of escape from the stream, so that that stream of electrons is kept concentrated and tightly focused to go on its target. Linux can be used to reach energies of, so Linux can reach energies of 50 giga electron volts. Now, the higher the energy that a particle accelerator can reach, the further it can probe into the inner workings of subatomic particles. And as physics has advanced, it's become necessary to build ever bigger and ever more powerful particle accelerators to explore things more deeply. But to get to this 50 giga electron volts, these particle accelerators need to be very, very big. One of the problems with Linux is that they are straight and they're really long. The shape allows them simple acceleration and avoids some of the issues that you have with synchrotrons. So a synchrotron is a circular particle accelerator, which we'll discuss, and we'll discuss some of the problems that they have. But because they're straight, they can't reach the same high energies that a circular particle accelerator can reach. It also means that if some of the electrons are not on in that focused beam, say they drift out of the beam, they won't hit the target and they're just lost. Whereas in a circular field, circular particle accelerator, those lost electrons or lost particles, whatever type of particle you're using, will just recirculate and it can be used again in another collision. So there's not that wastage of the particles. Because one thing to note is with these big particle accelerators, they're very expensive to run. Some particle accelerators even have their own power supplies that will power stations, little power stations attached to them to actually power these things, because the energies that they require are just phenomenal. So these were the first particle accelerators that were really built and used in research. We're now going to go on to cyclotrons. So a cyclotron, they were around about first developed in the 1930s, and these are circular particle accelerators. Now the first one was really quite simple. It was very small. This little cyclotron, although you can't really tell here from this picture, was so small it would fit in the palm of your hand, but it was only capable of very small energies. The system to build them were developed further, and they managed to get up to 18 meters in radius. Now the way that they work is, let me find our diagram for that. get rid of that and that. Here it is here. So this shows us how the cyclotron works. So what you've got here is you've got two here and here. I'll see if I can draw on top of it. It won't let me draw on top of it for some reason. So you've got these two metal boxes and they're in the shape of Ds. So this is called a Ds of the cyclotron. And these are supplied by a very high frequency alternating current. So the gap here has a very high potential difference. Now in the centre here you have a proton source. And the Ds are placed inside a really high magnetic field. So you'll have this magnetic field that's kind of uniform magnetic field, and the Ds are placed inside this magnetic field with their high frequency alternating current, and you've got your proton source here. And what happens is we use the magnetic field and it will drive the protons round and round in this circular motion. And each time it passes through this potential difference, it gains more speed until it gets the desired speed, and then there'll be a exit part here where the stream of protons can escape and then collide either with another stream of particles or with some target. The alternating supply frequency is matched to the movement of the particle, so the polarity reverses at the right time to cause the acceleration across the gap. So once the proton reaches the gap here, this will become negative, that'll become positive, so it's attracted to the positive side. Then it'll come round here, this will become negative, that'll become positive, and so on and so forth. So this gap is going to be where you see that acceleration from acceleration happening. Each time it rotates, it gains more energy. As a result, it will follow the semicircular path each time, and then it exits this as a high energy beam to be used in the collisions. So what are the problems with cyclotrons? Well, the problems that they have are dealt with in synchrocyclotrons. The problem that you get with these, because you're accelerating these particles to really high speeds, as they reach the speed of light, just like with the linear accelerator, you have relativistic effects that you need to take into consideration. You're going to see the mass increase as it reaches the speed of light, and that's therefore going to affect the path of the particle. However, these the cyclotrons, these simple circular particle accelerators, can reach up to 500 mega electron volts. Now that brings us on to our, see where, let's get rid of that one. This brings us on to our synchrotrons. So these are the particle accelerators that can get to the highest energies. They require large distances. So as a result, these particle accelerators are huge. Unlike the cyclotron, a synchrotron has a fixed radius, no matter what energy. Of the particle. So the frequency can be altered, the frequency of the supply can be altered, and the magnetic field as well, to maintain the path maintain the circular path, and correct for relativistic effects. So as you see the mass of the particles increase as they approach the speed of light, the magnetic field and the frequency of the supply can be altered, and that will take that into account, the changing mass. So the deflection caused by the magnetic field is what makes the path curved, while it's the frequency of the electric field change that increases the energy. Now, I'll do a wee diagram here. So you've got this kind of circular tube, meant to be a tube. And throughout it, I'll get different colours to make it clearer. So you'll have at different places around your accelerator, you'll have electric fields to accelerate the particles, just like on both the linear and the cyclotron, where you had the potential difference with to create that electric field that would accelerate the particles. Here you have certain points throughout the synchrotron that will create electric fields to do exactly the same thing, where the particles will be accelerated. Then you have, in other places, you have detectors. I'll say more about that in a minute. And then finally you will have points along the accelerator where you've got magnets, and these are used to bend and focus the beam. So the magnets will keep it on its circular path, and they'll also keep the beam focused so that you don't have particles drifting out. Now, as it goes round and round, you've got these detectors at different points, and you'll have different detectors depending on the experiments that you're running. Sometimes in these detectors you might have a fixed target, which you will collide your beam into once it reaches the desired energy, but often you will have two beams going in opposite directions, and then when you do that you can take the energy of each beam and the sum of those energies will be the energy that you get in your collision. So by doing two beams collided together, you're able to maximize the energy of your experiment. So currently, synchrotrons, I've changed my colour here, but never mind. Synchrotrons are capable of getting up to energies of 7 tera electron volts. Now, if you have one beam going with 7 tera electron volts in that way, and then another beam going the opposite way, that sum of that would give you a maximum of 14 tera electron volts, which is very high energy. Often these synchrotrons will have a linear particle accelerator attached to them. So you'll have a linear particle accelerator. Won't draw it there. So you often get a linear particle accelerator here, and then you'll have a beam of particles already accelerated to a high energy before it then enters the synchrotron. So it just helps get to higher energies. Radiation is emitted as these particles go round in very high energies. You get radiation emitted, and it causes a loss of energy as the particles are radially accelerated. There's different methods used to reduce this effect, but sometimes this radiation can be used in experiments themselves, and sometimes particle accelerators will be used to actually generate specific types of electromagnetic radiation. For example, specific frequencies of X-rays will be generated through particle accelerators. So the collision, we've talked about the detectors here and here. By placing magnets around the particle beam, it focuses them into this really slim stream that can be controlled by the magnetic field, and that allows the scientists to really accurately pinpoint where and when they want collisions to take place. If you think about it, you're smashing a stream of subatomic particles together. These are tiny things that you want to bash together. So the level of precision that is needed is really very high. If you Google you can Google what these detectors pick up, and it's really quite beautiful. Let's just clear this just now. So if you look at this picture here, this is a picture from a detector, and it's the tracks of after ions have been collided together inside a particle accelerator, and this is the aftermath of these collisions. And if you Google that, you'll see some really beautiful pictures that are worth having a wee look at. So the detectors, let me get another page up. So detectors use magnetic and electric fields to investigate the results of a collision. The detectors, they don't detect the actual particles. But the trace left behind as they ionize the area around them. The paths followed by the ionization of the detectors give details of the masses and the charges of the different particles. So by looking at those, I'll bring that back up again quickly. So by looking at these tracks that are produced, scientists are able to tell to deduce the mass and charges of different particles, and that's how they would find new particles. So from the first cyclotrons that were developed in the 1930s, there's now been many particle accelerators built purely for scientific research. So we looked at, let's get rid of that there. We looked at this one here in America. This is the linear accelerator at Stanford, USA, and it was 2 miles long. It was completed in 1966 and was used in the 1970s for the experimental evidence for the existence of quarks. In Tiverton in America, another cyclotron was responsible for the discovery of the top quark. The maximum energy of the Tiverton is 1 tera electron volt. But since then, in Europe, we have had the building of the Large Hadron Collider. And this is a picture of inside. It's a very famous image. It's a bit out of focus, but you can see down here, there is, this is the Large Hadron Collider. And here, if you look in there, you can actually see a man. So that gives, this is when it was being built. So this is a picture that can never be recreated because you can't go in it now because it's all enclosed. So this is when it was being built, and this is a man here to give you an idea of the scale of this thing. It's absolutely massive. It was a phenomenal piece of engineering when it was built. And it is in, let me see if I can, where's my other picture of it? Here it is here. So this here is an aerial picture of the Large Hadron Collider. This is 27 kilometres in circumference, and it straddles, it's mostly in Switzerland, but it also straddles the French border. That there's the French border, so it's a bit in France. And if you here and here, you see there's smaller accelerators. This is part of the CERN complex in Switzerland. And this is a collaboration of different countries across the world helped fund the building of this, and the expertise used was international, and it's been used to probe into new areas of physics, and the stuff that goes on here is really cutting edge. The protons can be accelerated to 7 tera of electron volts. So if you have 7 tera electron volts in that direction and 7 tera electron volts in this direction, the resulting collision is 14 tera electron volts. Oops, I've done that the wrong way round. It was the Large Hadron Collider was used to search for the Higgs boson, which was discovered in 2012. It's like the missing piece of the Standard Model, which we're going to come on to next, and confirmed experimentally a lot of the different parts of the Standard Model that were still to be verified through experiment. They hadn't been able to verify them up to that time because they didn't have a particle accelerator big enough. Now, if you can see, but before the LHC was built, there was particle accelerators. Here you see that Alice, CMS, and there's other things over here that are used. So this was already a complex that was doing particle physics before the LHC was built. Incidentally, this is also the most expensive science experiment that has ever been conducted. So I hope that all makes sense.